All right, so let me then just move on. What we want to do is that for rotational money, it's always good if you have a symmetry of your system. It's always good to use a coordinate system that is adapted to that symmetry. Okay, that makes it easier or more convenient to solve the differential equations. So because of that, we are going to write down the L operator in the spherical polar coordinates, okay? All right. All right. So remember that if I make a, we can do it in. Let's write down the L operator in Cartesian coordinates first. So remember that L is x cross p, right? And or minus I h bar x cross the gradient operator. Well, del. So now suppose that I do a rotation of the system around z-axis, okay? Then we know that the transformed wave function is related to the original wave function by e to the power minus alpha divided by h bar L of z acting on psi of x. Okay. Now, if alpha is a small angle, then I can write this as, I can write, say, the change of psi, which is psi prime minus of psi, is going to be minus I alpha by h bar Lz acting on psi of x. But what is Lz? Lz is minus I alpha by h bar x minus I h bar del y minus y minus I h bar, minus I h bar del by del x, okay? This thing acting on psi. So we want to transform this to the spherical polar coordinates. What are those coordinates? Let me define them. So this is the z-axis, and this is the y-axis, and this is the x-axis, okay? X, y, and z. And then this is some, position vector, and this angle is then theta. And if I take the projection of this vector onto the xy plane, and the length of this vector is r, then this length is r sine of theta, and the azimuthal angle phi, if this is phi, then then basically yeah. So these are our basic coordinates, right? Now, how are these? So x is going to be. So let me change color back to normal. Although I love writing in red. So x is this shadow, right? So x is going to be r sine of theta cosine of phi. Y is going to be r sine of theta sine of phi, because r is, that's y. And then z is going to be r cosine of phi. Not phi, theta, sorry. Okay? You agree, right? And we also need the inverse of these relationships. And they're not as pretty. The inverse is r is equal to x squared plus y squared plus z squared by Pythagoras, right? And phi is tan inverse y over x, and theta is tan inverse square root of x squared plus y squared divided by z. Okay? You guys agree with this?
Yes, sir.
Yeah, you should all know this. Yeah. Although, this is something you always forget, so you have to work this out. All right, so now we want to express this equation in polar coordinates. So, we can just like, use the, the chain rule to express these derivatives in terms of theta and phi. And for the operators other than LZ, that's basically what we have to do. But for LZ, there's a shortcut. There's probably a shortcut for the other ones too, but I haven't been able to figure it out. Okay. So if I do a rotation around z-axis, then of course what will happen is that psi prime r theta of phi is given by e to the power minus I alpha by h bar L of z psi of r theta and phi. And of course this should be equal to r phi of r theta of phi minus alpha. Only the angle phi should change, right? Because we're rotating around the z-axis. Now, if I do, for small alpha, if I do a Taylor expansion, I get psi of r theta of phi, and then I get a minus alpha del psi by del phi. And so then I can write del of psi is equal to minus I h bar del by del phi. Sorry, I can write this as minus alpha del psi by del phi. Okay. Now this I can write as in a clever form, and I can write it. I can compare it with this thing. So if I do an expansion to first order in alpha, I should be getting minus I alpha by h bar L of z acting on psi. So if I compare these two things now, I get that L of z is going to be minus I h bar del of del phi. Okay. So this is LZ in the spherical polar coordinates. Okay. All right. So now what about Lx and Ly? So Lx is I h bar y del by del z minus z del by del y, right? And then you basically have to calculate very boring stuff, but del by del z is del r by del z del by del r plus del theta by del z by del theta plus del phi by del z del by del phi. Okay, so using these relationships, you can now calculate these three quantities. And I am going to leave this as an exercise. Haha. Sure.
Sir, can the angular momentum algebra give a shortcut in any way? Though I haven't tried it.
Sorry, I couldn't hear you.
Can the angular momentum algebra provide any short route to deriving these, the rest of the components?
There is probably, but I haven't figured it out.
Okay, sir.
So if you can figure it out, please let me know, okay? I tried and I just couldn't. So, but I think there is, okay?
Okay, sir, I'll try it then.
Yeah, just try and let me know, okay? I think there is, and it should be, you mean there's a geometric way of deriving it? Yes, there is, should be a geometric way of deriving it. So, okay. So now if you then work this out, and it's just like a page of algebra, you get that. And of course, these are, I mean, I'm going to put some of these probably in either the tutorial or in the assignment, and which is good because then this is not difficult, it's just boring. But these are things that you have to do. You have to be able to do this kind of boring calculation if you want to be a physicist or a mathematician. And it's easy points because you just do it, okay? So Lx is then going to be, if you churn through the calculation and you make mistakes, then you get minus I h bar, and then I think there's a minus sign. Hang on. Yeah, minus sign. Minus sign of phi del by del theta minus cot of theta cos of phi del by del phi. Okay. And similarly, Ly is going to give you minus IH bar, but here you get a plus of cos of phi, and then del of del theta minus cot of theta sine of phi del by del phi. And if you work out what L plus minuses are, the raising and the lowering operator, you get minus I h bar e to the power plus minus I of phi, and then plus minus I del by del theta minus cot del by del phi. So it's actually much more simple, okay? And then you can say, okay, I want to calculate what L squared is. L squared, if you remember, is Lz squared plus half L plus L minus plus L minus L plus, okay? If you plug that in, if you plug in those expressions, you get minus a squared 1 over sine squared theta del squared del phi squared plus 1 over sine of theta times del by del theta in bracket sine of theta del by del theta, okay? Now, if you have done calculus, your calculus courses, or where you're taught curvilinear coordinates, then this should be ringing some bells, because up to factors of h squared and factors of r, this is, and not factors of r, factors of r and plus minus some stuff. L squared is essentially the Laplacian plus some stuff, okay? So which means that we should be able to express our Schrodinger equation in terms of L squared, which would make life significantly more simple for systems of analyzing systems which have spherical symmetry. Okay. Any questions?